Okay, Bismillah ar-Rahim. This is the third lecture. First lecture was just introduction. The second lecture we got started on digital filters. Now in this lecture we're going to go over what we had last time, just a quick review of the digital filter experiments that we did last time. And then I'm going to just explain to you some theoretical background on digital filters so that you understand the difference between FIR and IIR and things of that sort. And you can explain also the transient that you see at the beginning of the output of the digital filter. And basically after that, we're going to discuss the comparison between FIR and IIR, okay? Of course, this will come in the theoretical review. Basically, there are theoretical differences between the two, of course, but we can also see the differences when we run experiments using both types of filters. So basically, we're going to design the same filter, basically the same filter specifications will be used to design an FIR filter and IIR filter. And we see the output and basically try to judge the difference between the two types experimentally. Then, in order for us to start working with real data, before we got started with real data, because actually we don't really know the kind of artifacts that we have, we are not really sure what their parameters are, and basically it's very difficult for us to design a filter. At least we don't really know the specifications of the filters that would be suitable for them. We're going to do some simulations, a little bit more advanced simulations, where we simulate a 60 Hertz noise on ECG. Last time we did simulations of two sinusoidal signals added together, and we filtered one out of the mixture. Now we're going to have a simulated 60 Hertz noise on ECG. Basically, this happens when you have a poor filter in your ECG, and basically some of the noise from the AC that is in the examination room would actually be superimposed on your ECG. So we're going to simulate that. Basically, we're going to generate a signal that has these characteristics. And basically, the reason why we're going to work with data like this, because in this case, we know exactly the frequency of the noise. We know that the noise is at 60 Hertz. So basically, we're going to get started on designing suitable filters for that. And the difference would be that we're going to be working with ECG. The actual signal that we would like to recover is ECG, very similar to what we're going to do in the research project one. So basically, after we simulate that, we're going to get started on some experiments to design filters for that. And then we will move on to get started on the real data we have. We're going to start with the baseline wonder artifact and basically try to estimate the baseline wonder characteristics from the data and try to start on the experiments on filtering the baseline wonder artifact from the ECG data. Okay, so these are the things that we're going to do today. You have any questions about any of them?
It's okay, Doctor.
Okay, so now I'm going to share the screen so that you can see Matlab. Okay, you see Matlab now?
Yes.
You see Matlab? Oh, okay. So last time, let me go over the code that we had last time. Basically, we simulated two sinusoidal signals. As we said last time, the simulation of a sinusoidal signal, maybe you can get back to review it here. Basically, if you have a sinusoidal signal, the sinusoidal signal will be basically like any sinusoidal signal will be S of t, for example, is equal to sine twice pi f note t. Okay, this is as a function of time. We don't really need to have time here. We need to have it in discrete form. So t would be basically NTS, where TS is the sampling period. Okay, so basically we're going to replace this. Basically, we just replace each t by NTS. So we basically will have S of n, because TS is constant. So basically everything would be a function of n, would be equal to sine twice pi F naught, which is the frequency of the sinusoidal we would like to have, times Ts. And Ts by definition is 1 over Fs, the sampling frequency. Okay, so basically if we said that the sampling frequency is whatever, so let's go get to the code and see how we implement that. So basically I define each one of these parameters and then simulate the data. Just put n 0, 1, 2, 3, so on to the number of points that I would like to have. So see here, I have Fs is equal to 200. Actually, I commented out this part here because actually it's already there. Okay, and Ts is equal to 1 over Fs. The number of points I'm going to simulate is 200. I can change that. It's just a matter of my choice. And then the n, the small n, which is the time variable, will be 0, 1, 2, 3, 4, and until n minus 1. From 0 to n minus 1, you have n points, which is 200 points, the number of points that I selected. I simulated two frequencies. Frequency F1 is equal to 10, and frequency F2 is equal to 30. Okay, so basically each one of them will be exactly the equation that we just talked about. Sine twice pi F1, instead of F naught, you have F1 here, and in the other one you have F2 times n times Ts. So basically this will be the first one, this will be the second one. Okay, and then I'm going to add them together. I'm just going to add the two frequencies together. We have 10 hertz and 30 hertz signals added together. I plot them and basically filter one out of the other. Basically, the upper part here is the filter that I generated from the filter designer tool in Matlab. It designs a filter with a pass frequency of 20 and the stop frequency of 29. So basically, if you see the two frequencies here, if you have a low-pass filter with cutoff frequency 20, you expect it to keep all frequencies below 20 and remove any frequencies above the f-stop, which is 29. So it means that the first frequency will stay, the second frequency will be removed. Let's run it first and then go to the part where we generated the code. See here, this is the first signal. This is the second signal, which is the high frequency 30 hertz. This is the addition of the two. After I filtered with a filter with cutoff 20, basically I recover the first signal. This is just a basic digital filter that we tried last time. Okay, let me go review also the part about the filter designer tool where I generated the first part. What I exactly did was just use a filter designer. This is one of the tools that are available in Matlab. Just write filter designer. And basically, you're going to come up with basically something like an interface that looks like this. Basically, here you're going to put the sampling frequency, which is basically we assume that it's 200. The F-pass, this is a low-pass filter. I chose here a low-pass filter. So basically, I chose, I have to choose the pass frequency and the stop frequency. The pass frequency determines the range of from 0 to the frequency where the signal, the input signal will come out exactly the same as the input. From the stop band, from the stop frequency, anything above the stop frequency will be completely removed or be attenuated with this much attenuation here. So basically we chose F-pass equal to 10, F-stop is equal to, let's just say here 25 to have a different frequency. And here if you have choose the decibel scale, we accept here variations around 1 decibel. Remember that the pass frequency here, you have 3 decibel frequency, 3 decibel attenuation at the pass frequency, as the F cutoff. If you remember the cutoff frequency for the filter, we call it a 3 dB frequency, which means that the signal will be attenuated by 3 decibels at the cutoff frequency. So if I chose 1 decibel, it means that the whole range here will be attenuated less than 1 decibel, which is very good, okay? For the A-stop, you decide how much attenuation you need between this and this. So basically, if I say that it's 80 decibel, it means that, if you remember from last time, 20 decibels means 10. 40 decibels means 100. 60 means 1000 because it's a logarithmic. Yes, it's a log scale. It's 20 log amplitude. So basically, if you have 80 decibels, you have 10,000. Okay, let's make it a little bit less because actually we don't need it that much actually. So basically, if you do it like this, so basically you're going to design a filter with these specifications. And basically, it's going to give you the response of the filter that looks like this, okay? If you see here, you have almost all parts of the stop band after 25. It's basically around or less than 40 decibels. The range here that you're interested in is very close to 0. 0 is basically 1 because 20 log 1 is 0. So basically, here in the pass band, it's almost 1 everywhere. Okay, so basically this is the filter that we generated. Okay, what we did last time to take this filter and use it was to basically go here and say generate Matlab code, and we basically select filter design function. Okay, filter design function will give you the function that is used to basically design this filter. So I'll just say that leg2 or leg3 LPF1. Okay, so that we know that this is the filter that we did today. You will get a function that looks like this. What we said was basically instead of calling this function, I'm going to do something a little bit better actually. I'm just going to comment out this here so that this becomes a regular Matlab code, and then I'm going to copy the part where I had the simulation. This is the part where I simulated my data here. I'm just going to copy that and put it here. The filter, the design filter, comes out in this variable here. This is the variable that contains the filter. This is the filter that I generated after this design procedure. All the specifications that I selected are here, and the filter comes out in HD. Whenever I do the filtering here, I'm just going to say filter HD. I just select the parameters or the filter design that I already did and just put the signal that I would like to filter. Okay, so basically here what I did here was just FS here was commented out because it's already there, because this is one of the specifications that I gave in the filter design. But it's fine if you want to keep it, it's fine. You can just keep it. Doesn't matter if you keep it like this, it's not going to change anything. So basically this will basically first design the filter and then simulate the signal and then filter, do the filtration and basically plot the output. Let's try that. It's exactly the same like the one we saw before. But actually the first part here looks a little bit nicer actually. So once we change anything here, instead of having to go through the filter designer, changing parameters here and generating another filter and basically doing the same thing over and over again, it's much easier here because it changed things here. I can change whatever I want here. Okay, so basically if I say fpass here is 20 and fstop is 25, I can just basically generate the filter right away after I do that. It's obvious basically that let me just put the N here, sorry. The filter order here comes in N. So let's just try to see how much the order of the filter comes out like. N here is 57. The one that we saw before was 19. Okay, so this is much longer. And the longer the filter, the higher the order of the filter. This is the order of the filter. You will see that in the output, you will see that it's basically the transient becomes a little bit longer. You will find out maybe by the end of this lecture or probably next lecture that this transient actually is equal to n over 2. So the order of the filter over 2 will basically give you the number of points at the beginning of the filtered signal that are what we call transient. Transient meaning that it doesn't look like the signal. Basically, the filter is still basically processing until it reaches the steady state. Whenever it reaches the steady state, it becomes very stable after that. But in the first part, the first n over 2 points, you're going to find this problem here. So it's easier to do it this way because I change the parameters. So for example, if I put this as 29, okay, you're going to see something a little bit different here. See the difference here? It's shorter. The order of the filter is 31, meaning that you have only 15 points of transient in the figure here, okay, which is almost right here. 15 points of transient, which is shorter than what we saw before. So this helps you, if you do it this way, this will help you optimize the parameters of the filter just here, right here, instead of having to go back and forth between the filter designer tool and your code. And each time you generate a new code and copy this part here and try again, you don't want to do that. Okay, you just do it once, do the design once, and then change the parameters for the same design on this file, and that's it. This is actually what we did last time. Do you have any questions about how to do that?
So this design, the code is for only low pass filter, right, doctor?
This is a low pass filter, right? Right. Once you decide it's a low pass filter, basically you have to do it. If you decide to use another type of filter, then you will generate another file and optimize in that file. Okay. So basically, this is for the particular type that you decided it will be suitable for your problem. Just one type. You cannot change it to become band pass you can do that, but actually it's easier to just generate one band pass and just optimize over that one band pass.
I'm curious about the repo of the filter. Why there's a repo in the filter?
Actually, we're going to talk about it now because basically, let's go over the theoretical part, and then you will basically get it from the theoretical part.
Okay.
Do you have any questions, other guys?
Thank you, Doctor.
Okay, so we're going to talk now about the theory of basically the filtration in general, the digital filters. Okay, so basically we start with x of n. Now we're talking about x of n because it's a discrete signal, okay? And we're talking about a discrete filter. We're not talking about an analog filter, okay? And you want to get y of n that meets certain specifications, okay? So basically, this is what you saw before, okay? Basically, if you want to talk about a system, sorry. Okay, you basically have an input of x and you have an output of y. And we used to call it h, if you remember. This is a system, okay? And we used to call the specification or the impulse response of this system h of n, okay? And we'd like to estimate that h of n to meet certain specifications. Basically, I just want to, first of all, describe the characteristics of this system, okay? So first of all, we are concerned with something called linear, time invariant systems, okay? So basically it's linear and time invariant. And basically what we are doing here through the filter designer tool is to design a filter that meets both. The linearity, actually, if you talk about the linearity, the specification or the criteria that determines linearity is basically based on what's called superposition. And things that you probably saw in the signal systems course, your undergraduate course, but actually it's very important to have that concept actually here. So basic superposition had two things: additivity and scaling. Additivity means that if you have here x of n, let's just put another, if you have x1 producing y1, and you have x2, another signal, on the same system, passed to the same system, whenever you pass it through the system, you get y2. If you have x1 plus x2, it will produce y1 plus y2. This is the additivity. This is a characteristic, a very important characteristic of linear systems. If you have x1 producing y1 and x2 producing y2, and when you add them together, doesn't give you the addition of the two outputs, then this is not a linear system. Okay, let me give you an example. If you have something like a system that would be like a system like that looks like y is equal to x plus 1. Okay, so if you have a system that looks like that, basically, by the way, any system is described by an equation of y as a function of x. So any equation you see where y is a function of x, this is a system, basically. Okay, the system input is x and the system output is y. So if you look at something that looks like this, basically y1 would be equal to what? x1 plus 1. System 2, if you input x2, you will have something that looks like this, right? Let's try to have an input of x1 plus x2. So basically, replace this with x1 plus x2. This would be what? x1 plus x2 plus 1, right? Would that be equal to y1 plus y2? Can you answer me?
No, doctor.
Yes. Y1,
No,
yes.
it should be 2 plus 2.
Right. Because of this one here screwed up everything. Why? Because basically, if you have x1 plus x2, if this is equal to x1, y1 is equal to x1 plus 1, this is equal to x2 plus 1. When you add them together, it's going to be x1 plus x2 plus 2. So basically, this is wrong. So basically, this is not a linear system. So even though the equation looks very nice, this looks like a linear curve, right? It looks like a linear curve, right?
It's linear.
It looks like a linear curve, but actually, from the point of view of systems, this is not a linear system. Basically, in order for you to have a linear system with a linear equation like this, you have to basically have a system that passes through zero. So basically, if you draw it, basically, it has to be like this. It has to pass through zero. Okay? If you have a line that looks like this, or a line that looks like this, these will not be linear systems. Okay? So it has to pass through zero. When x is 0, y is 0. Okay? Otherwise, this is x and this is y. Otherwise, it will not be linear. Okay? So this is very important thing to take care of. Okay? So this is the additivity. This is the additivity test. Okay? We worry about these things because remember that we assume that the signal is contaminated with additive noise. So the input to the system, the filter is a system, and the input to that system is the addition of two signals. One of them is the true signal, and the other one is the noise. If you don't have a linear filter, the problem is that the dealing with the two components will not be exactly the same. Basically, you can have distortion from the noise still coming out on top of the true signal. So you want to have separation, meaning that you assume that the output from the true signal basically does not depend on the output from the noise. So basically, if the filter is working to pass the true signal, this passing of the true signal will not affect the rejection of the noise signal. The other criteria for linear systems is the scaling. Scaling means if I have X producing Y through our H, then if I multiply X by alpha, it will produce alpha times Y. The same factor here multiplied by that here. Okay, sorry, yes, exactly the same. This is very important, okay, because basically what we would like to have, basically, if I consider the filtration of a signal, okay, the low-pass filter, as we talked about last time, would look like normally something like this. You have certain part of the spectrum passing, this passes, and the other one doesn't pass. So basically it passes here, it doesn't pass here, okay? So basically you multiply your signal by this value here. This is 1, okay? And this is 0, okay? So basically if you have your filter looking like this, so if you multiply a component by 0, it has to actually produce a 0 at the output. Otherwise, this will not be satisfied, okay? So if we consider the same system that we were talking about above here, that's just to consider the same system and check if it's linear or not. So basically, if I have also system Y is equal to X plus 1, just insert here alpha X. So if I insert here alpha X, just put here alpha. So this is Y equal to this. If I have alpha X plus 1, okay, can you put brackets here so that it becomes alpha Y? Can you do that? If I have, instead of X, I have alpha X.
No, can't.
No, sorry. 1 alpha.
Can you take alpha as a common factor between alpha X plus 1? You can't. Basically, you're not able to do it. If you have alpha X plus 1, if you take alpha as a common factor, this will be X plus 1 over alpha. This is not Y.
Right.
So basically, this does not satisfy the scaling property. Okay, so basically, this is the basics of linear systems. Let's get into the actual filters, how filters are done. Let's take several examples. Basically, the filter by definition in digital filters, you basically have Y as a function of X. Okay, in digital form, this can be something that looks like this. Y of n is equal to X of n plus X of n minus 1 plus X of n minus 2, for example. Okay, basically the input is the Y values, the X values, and the output is the Y values. Okay, and here I'm computing Y at n from X at n and the previous values of X. Okay, this is a simple example. This is basically one of the filters that you can see. This is basically called, if you multiply by a factor, you can call it actually a moving average. Okay, this is a system actually. This actually represents a filter. Okay, and basically the way we compute this, okay, is basically it's extremely simple. So basically what you do here is just use substitution basically. You just basically, if I have X of n, if I want to, for example, compute the impulse response. What is the impulse response? The impulse response is the output for something that looks like an impulse. An impulse would look like this, basically. Okay, this is the impulse. Basically at 0, here it's at 0, and the other values here are zeros. Okay, and this is 1 here. This is X of n. If I say that I would like to compute the impulse response with something that looks like this, this means that X of n is exactly an impulse. This is what's called unit pulse function. This is the discrete version of the impulse. Okay, so how can we do that? Basically, we have Y of n here as a function of X of n minus 1, and so on. Let's try to compute Y at negative 1. Y of negative 1 is equal to what? Can you tell me exactly what the expression for y of minus 1? Just substitute here n equal to minus 1.
Minus 1
X of minus 1
plus x minus 2, x minus 3.
Sorry.
Okay. How much are these from this here? This is x of n. So basically, this is minus 1, this is minus 2,
0.
this is 2, this will be 0. Right. How about y of 1?
X
1.
X of 0.
X
So
1.
0.
So,
1.
N is x of 0, sorry.
0. Okay.
0.
So 0 plus x of minus 1 plus
Minus
x
1.
minus 2. This is 0, this is 0, this is what? This is 1.
This is 1.
1.
So it's going to be equal to 1. So
Yes.
basically, it's basically the kind of equations that look like this actually are called difference equations. And the difference equations are the discrete version of the differential equations. Okay? So instead of having to solve them analytically like what we used to do in differential equations, we can just solve them numerically like this. Okay? With just basically substitution, basically. That's it. So how about y of 1? Let's go back. Y of 1. X of 1.
X
1 plus 0.
X of minus 1. This is 0, this is 0, this is 1. So it's going to be 1. How about y of 2? X of 2. X of 1 plus
and
x
of
of 0. This is x of 0, this is 1, and this is 0, this is 0. So this will be also 1. How about x of 3 and anything after that? Here you're going to have x of 3, x of 2, plus x of 1. Are any of these non-zero? Basically, you just consider this. Basically, x of n is 0 anywhere after 0. It's only 1 at 0. Okay? So any value for x of n after 0 at 1, 2, 3, 4, any number, any positive number or any negative number will be 0. So basically the output here will be what?
0.
0 and will continue to be 0. So the output here has only 3 non-zero values. Right? Only 3 non-zero values. Other than that, everything is basically 0. Okay? If you look at the form that we have here, how many terms did we have here for x?
3.
We have 3 terms. And we have here 3 terms. Actually, this is a type of filter that we call finite impulse response filter. Finite impulse response means that h of n, which is basically what we produce here is h of n actually. This is the impulse response. Basically, h of n is basically equal to y of n for x of n equal to delta of n. Whenever you have the input as impulse, unit impulse, basically the output will be exactly h of n, the impulse response, which is by definition, basically, I call it impulse response. It's basically the output of the system when you put an impulse at the input. Okay, so basically the impulse response here is finite, meaning that it has only limited number of non-zero outputs. It has only 3 ones, and before and after that it's 0. Okay, so that's why we call it finite impulse response filter. Finite impulse response filter, or FIR. Okay, so the thing that we just saw here, if we go back to Matlab for the filter designer, see here, we have FIR or IIR. We're going to talk about IIR in a second, okay? But see here, this is FIR. This is exactly what we were talking about. And the order here is 19, okay? Meaning that the impulse response will have a maximum of 19 non-zero outputs. Okay, but actually the actual filter design is, if you want to consider something that looks like exactly what we have here, it's basically assuming that we're going to have, for each one of these, we're going to have a certain factor here. We're going to have, for example, A0, A1, A2, and basically the design of these will basically constitute the filter design that we actually do. So the filter designer produces the values of A0, A1, A2, A3, whatever, according to the order of the filter, and basically it's exactly this equation, and the output is computed in exactly the same way. Okay, it's very easy for a computer to do that because basically it's just a matter of substitution. Okay, so this kind of filters, whenever you have y of n as a function of x of n like this, it's very easy to see that this will become a finite impulse response filter, because basically it's a linear. It's first of all, it's linear. Okay, whenever you have summation of x's, it's still linear as long as it doesn't have constants or it doesn't have x times x. If you have x of n times x of n minus 1, this would be like x squared. If you have y equal to x squared, it's going to be a quadratic shape. It's not going to look like a linear curve. Okay, so basically this kind of design is called finite impulse response filter. Okay, the reason why we have the transient that we just saw is because basically, imagine how you're computing that. Basically, whenever you compute the output, y of n, the output is computed as y of n is equal to x of n convolved with h of n. So basically, you're going to be convolving whatever input you have with something that looks like, if we look at exactly what we had from the output of this filter, it looks like this, like sorry. Okay, you have something that looks like this. You have this 1, 1, 1, and the other points here are zeros. Okay, but you're convolving whatever x, whatever you have. If you have something that looks like whatever, something that looks like this. Okay. Okay, you have to convolve these. The convolution, by definition, you just take that and put it here and multiply it and then shift it and so on. Okay, the problem is, imagine that you're going to do that with this kind of filter. The first node point that you're going to compute will look like this. Okay, you have points here, here, here. This will be multiplied by this, right? The point is here that the points here, if you have zero points here, basically, if you have the data starting from this point, you don't have any data here, no data. This will be multiplied by this, and these will be multiplied by 0. So basically, this will, the 3 points here will not be multiplied by 3 points from the data. No, it's only 1 point data, and the others will be zeros. So basically, you're not going to be able to get the real data or the real results if you just shift it by 1. Basically, the second one would be like this. 3 points would be like this. Okay, the third one will be like this. Okay. Okay, so here you still have only, you're going to be multiplying only 2 points. You're not going to be able to get the actual result or the correct result from your filter until you basically have the 3 points multiplying 3 points from your actual data. Okay, So basically here you're gonna get started. You're gonna get actual results that are coming from your data. Before that, you didn't get the results. Go ahead. Go ahead if you have questions. So basically at the beginning, basically the filter will start here to get the first point at 0, and this is at 1, and this is at 2. Okay, so basically whenever you have 0 and 1, you have a problem, because basically the filter is basically starting with only 1 point of overlap between the filter and the actual signal. So basically 2 points of your filter will be multiplied by 0. So basically you're going to get something that doesn't look like the data you have. Okay, here also 2 points will be multiplied, or 1 point will be multiplied by 0. This point here will be still multiplied by 0. So basically you're not going to get that. Here it didn't get that or that. You're still going to get something that is close, but actually it's not going to be exactly the output you expect. The only point where you get something you expect is basically when you have your data, your filter deep enough so that you can get this kind of overlap between your filter and your data. Okay? So basically that's why, if you see here, if the filter order was 3, so basically 0 and 1 were not okay. 1.5, which is n over 2, basically we did not have point at 1.5, but actually at 2, you actually got right. So basically, before n over 2, you didn't get correct results. After n over 2, you got the correct result. That's why.
That means the vector shift by 2.
Please repeat again the question.
That's mean we are shifting the by 2.
Basically, the first transient that we saw is basically n over 2, and it's a result of the fact that the linear filtration will assume that you have zeros before the data you have. Okay, so basically the filter, when you try to compute the first points, the first few points, you're going to have some parts of your filter not multiplying or not using real data from your data. It's going to be basically multiplying by zeros.
Right.
So basically, until you have all your filter points overlapping overlapping your data, you're not going to be able to get good results. So, and this actually happens at n over 2, because basically what you assume is that you have a filter that is usually basically you have as many points here as here. Okay, so this is the 0, so it's symmetric. Okay, so basically you start from 0 here, and basically you have to get these n over 2 shifted, okay, so that you can get all of the points in the filter multiplying your data. So this is the reason for the transient that you see. Okay, it's a matter of assuming, or basically the basic assumption, if you have a limited amount of data, that the filter has to basically move a number of points until it overlaps, all the points in the filter overlap the actual signal, so that you can get good results, get the actual result, the correct results. Before that, you have at least 1 point of the filter overlapping 0. And basically, when this happens, you're not filtering your actual signal, you're filtering something that is a little bit distorted. A part of the filter is multiplying your signal, and another part, the remaining part of the filter is multiplying zeros. That's why you get the transient.
Excuse me.
Go ahead.
The last one, is it multiplied by 2 or 3?
This one here?
Yeah, this one.
Basically, it's multiplied 3 actually, because basically you move this will correspond. I'm sorry, this is supposed to be here. Okay.
Yeah.
Supposed to be here. Okay. Sorry. Maybe you can delete that. Okay. So this is basically when you have the 3. Basically these 3. Okay. But you get the idea. You get the idea?
Yes.
Okay. So this is the first type of filters. There's another type of filters. This other type of filters actually happens when you have what's called a recursive system. The recursive system you have also y of n as a function of x of n, okay? Plus x of n minus 1, for example, okay? But actually, it's not just function of these, it's also function of, for example, 0.5 y of n minus 1. So basically, you can just move that. Basically, if you put equal here, this will be like this, okay? Y of n is not only a function of x of n, no, it's also a function of the past values of y, okay? This is still a linear system, by the way, okay? As long as you have y is here multiplied by constant and x is here, just x's multiplied by constants, it's a linear system, but it's called a recursive system, okay? Or what we're going to say about it now, infinite impulse response system, okay? Let's try an example so that you can see it clearly, okay? Let's just take a small example. Y of n is equal to minus 0.5 y of n minus 1 plus x of n, okay? It's just to make it a little bit smaller, okay? And also I assume that x of n is equal to delta of n, which means that it's equal to 1 when n is equal to 0 and 0 otherwise, okay? And whenever you have a system that looks like this, you have to have initial conditions for y, okay? Let's assume that the initial condition for y at minus 1 was 0. Basically, we started with a system that was at 0. The output was at 0. Let's try to compute recursively the outputs of this system, okay? So if you have a system like this, let's compute y of 0. Y of 0 is equal to what? Minus 0.5. How much is y of minus 1?
0.
0, which is multiplying 0 here, plus x of n, x of 0
So 0 is 1.
is 1. So basically, it's going to be equal to 1.
1,
okay? Yeah. If we had y of n is equal to x of n, then y of 1 would be equal to x of 1, which is 0, okay? So basically, if we have a system that was y of n equal to x of n, then the output would be 1 only at 0. But let's see here what's happening. What's going to happen? Y of 1 is equal to what? Minus 0.5 times y of 0. Y of 0 is equal to what?
1.
1. Okay, so now, and plus 0, right? So basically, this will be equal to 0.5.
Yes.
How about y of 2? It's going to be minus 0.5 times
1.
No, y of 1, because basically here n minus 1, so n is 2
minus 0.
Minus 0.5.
5. Yeah.
Plus also 0, which is going to be what?
0.
Plus?
Plus
0.25. Okay, so basically x of n gone. Okay, x of n is not going to appear anymore. It's going to be 0 all the time. But actually, the actual output now, okay, is coming from the previous output. It's a function of the previous. Each time, the output will be basically minus 0.5 times the previous output. So basically, y of 3 will be equal to what? Minus 0.5 times this. Okay, so it's going to be like what? Minus 0.125. And each time you're going to be basically divided by 2 and multiplied by a negative number. Okay, so basically this will be plus 0.0625, right? And so on. Okay, you see when y will be 0, will y of n be equal to 0 at any n?
النساوي
No, doctor.
Think about it. You have a number that is non-zero, okay? Each time you divide it by 2. Will it ever be 0? Actually, no, because it's a real number.
Yeah.
It's a real number. You're gonna keep dividing, and it's never gonna be 0. It's gonna be very small. Definitely, gonna be very small. It's already 1/4 is very small, but actually, it's never gonna be 0.
Right.
So this means that we had an input x that looks like basically an impulse, just an impulse, just very finite, okay, finite response, okay, and it produced output at y that looks like this forever. It's never going to be 0, okay. You can compute it at 1 million and it's still going to be not 0, okay. It's going to be very small, but it's not going to be 0, okay. So the output here is infinite. Infinite means that it's never going to go to 0. You have no bound on n. After that, it will become 0. It's never going to be like that. Okay. Finite means that you have a limit on n. After this n number, every output will be 0. Okay. Infinite means that you don't have that limit. Okay. N can be, if I say, for example, I have a system that becomes 0 after 10 billion points. This is still finite impulse response. Okay, because regardless of how large that number is, I have a limit. But for infinite impulse response filters or infinite impulse response systems, basically you're not going to have that limit. So basically, this is one type of system that will never die out. Output never 0. Okay, the output will never be 0. Okay, it's going to be very small, but not 0. Okay, so if you consider this filter compared to FIR looks much simpler. You know exactly when it's going to be 0. You don't have any problems with this. And basically, imagine that you have a system that would produce an infinite number of response points. And basically, you're not going to have only one impulse for a practical system. Otherwise, it would not be practical. Basically, I have to use it on signals. Imagine that you have an infinite response from one point and another from one signal, and another infinite response from another infinite response from another. You have multiple inputs coming in all the time. Basically, you might think of a possibility that the summation of these responses will be infinite at a certain point. Okay, and this will be a problem. This will actually cause you something called a stability problem. Okay, then there must be a reason why people are considering infinite impulse response filters or infinite impulse response systems in spite of the seemingly difficult or more unpredictable behavior of its solution. Okay, there are definite advantages of using IIR filters. Okay, so basically IIR filters will design something that looks like this. Okay, it will have two components. Component coming from the input and component coming from the previous values of the output. Okay, before we leave this and try to go and see some experiments, let me give you the usual expression of such filters in the Z transform. Basically, the Z transform is just a matter of convenience. Basically, you have the system definition already like what you saw, but instead of having, for example, x of n minus 1, I'm just going to say that when I convert it to Z with Z transform, this will be x of Z, and each one of these delays will be just Z to the minus 1. If I have y of n to the minus 2, for example, this will become 1.
Square.
Y of Z. Okay, So basically, this will make things a little bit easier so that we can describe the system in terms of what's called transfer function. And this transfer function is what is estimated by the actual filter design function. The transfer function, if we take, for example, the same equation that we talked about above here, okay? Just this equation here, okay? This equation, okay? Let's see how it looks like in the Z transform. You'll find that it's extremely simple. Basically, you're talking about something that looks like this. If you have y of n is equal to minus 0.5 y of n minus 1 plus x of n. Just take the Z transform, this will be y of z equal to minus 0.5 z minus 1 y of z plus x of z. The transfer function basically is called h of z, which is basically the Z transform of h of n would be equal to what? Just try to see what y of z over x of z looks like. Here, in order for you to do that, you have to basically take that to the other side here and take y of z as a common factor. This will be what? It will be 1 minus 0.5 z minus 1. And the other one here, x of z, so this plus.
Said it's become set
Just
up.
one. What?
Okay.
So basically, this will become just a simple equation in Z, okay? And basically, whenever you have something that has a numerator and denominator, bast wa maqam, okay? This will be IIR. Let's take the example of the other system that we talked about before. Y of n is equal to x of n plus x of n minus 1 plus x of n minus 2. This will be y of z is equal to
X of z.
yes, okay. Can we take it as a common factor right away? X of z times 1 plus
Z minus 1, X of z minus 2.
So basically, h of z is equal to what? Just divide this by this.
It would be 1 plus 1 for
Right, 1 plus z minus 1 plus z minus 2. So whenever you have a system that doesn't have a denominator, you have only just the numerator, okay, this will be FIR filter. And this is IR, okay? So as you see here, basically whenever you have a denominator, you run into the possibility if z is equal to, for example, 2. What would happen here if z is equal to 2?
2?
This would be
minus 1. Minus 1.
Infinite.
This would be 0 here, if z is equal to 2, right? Yeah. So basically, this is
infinity.
Stability.
Okay, so it's obvious that the IIR has obviously some problems, okay? Then why we are interested in IIR, okay? The reason why we're interested in IIR will be very clear when we go back here to the filter designer and basically see the response of the IIR. Just choose here IIR and see, okay? Let's put the specification that we put in the other one so that we can get a higher order. This is 20 and this is 25. We design a filter. The filter order here is 57, okay? Let's choose IIR, okay, and see, okay? The same exact specifications are there, okay? See the order here? It's 22. So instead of 57, you came up with a filter that has the same characteristics with basically less than half of the order of the FIR filters. In fact, when we get into the experiments that we are going to do for our real data, you will find that sometimes you get a filter order of more than 1,000. more than 1000 for the FIR, okay? And you can get almost the same characteristics with 1/10, 1/10 of that order using IIR filters. So the IIR filters are much more efficient than the FIR filter. Remember that what we talked about last time is that the order is proportional to the complexity of the filter. So the number of equations, the number of calculations that you have to do for each point output of the system will be equal to that order. And also the transient of the system will be basically half of that. Whenever you reduce the order, you have a simpler filter that needs less computation and produces less transient. Okay, so this is definitely an advantage. On the other side, you can find some cases where we're actually going to run into them actually when we try to do the experiments. And whenever you try to do more experiments, you're going to find out that in some cases, the IIR filters might actually be unstable. When you try to design a filter that is really complicated, sometimes the IIR filters will not give you a good result. Okay, so but actually you have to judge that for yourself. You have to definitely try to design FIR filters and IIR filters and compare the outputs between the two so that you can determine whether you can actually use the efficient implementation of the IIR or not. Is that clear? First of all, do you know the difference between FIR and IIR now?
Yeah.
We got it.
Okay. Do you know the reason for the transient that happened at the beginning of the signal? Whenever I do filtration, you expect to have transient. Do you know the origin of this transient and how long it will be? You know the theoretical basis for that? Okay, so basically these things I would like you to try and basically do experiments and try to match what you understand to the experiments, the outputs of these experiments. And if you have any questions, please let me know, okay? Because basically this course will be best if you actually combine the practical experience with the theoretical background. If you do that, you will never forget this concept, first of all, and you will be able to do much more with the theory than when you just don't understand the difference between the different concepts, or basically cannot relate the practical experiments to the theoretical background. Okay? Do you have any questions?
So both of them will also have a transient response, Doctor. IIR and FIR.
Yeah, they are both digital filters, yes.
Both have the transient effect.
Definitely they do, because basically you have the same problem, because you have the length of the filter, and the length of the filter you have to basically have that whole length inside your signal in order for you to get the correct output. So as long as the order is large, so basically you're going to have transient. So basically both will have transients definitely. But actually the transient in the IIR basically theoretically doesn't end, okay? Because basically the impulse response is just infinite, but practically you're going to see a very similar effect to what you see in the FIR because of very small values. Very small values are very trivial. Basically, you're not going to see them on your signal. If you have, for example, 1 millionth, 1/1 million, okay, added to a signal with amplitude of 1, you're not going to be able to see it actually. So basically, there are some hidden effects or some theoretical transients that are still present in the IIR, but practically they will behave very much like the FIR filters in that regard. Okay? Okay. So we're gonna move on. We already finished the first 3 parts. Basically, we're going to start now doing simulated experiments on the 60 hertz noise on ECG. So basically, we're going to simulate 60 hertz noise and use that on ECG to basically have a signal with noise to try and basically apply a filter and see whether we can actually get the ECG signal back or not. As I said at the beginning of the lecture, would you like to have a break in the middle, or can we continue to finish early? It's up to you. It's basically up to you. I can continue. I can give a break. It's up to you.
Continue, sir.
Okay, is that okay for all of you?
Yes, continue, please.
Yes,
This
it's
one.
fine. Let's continue.
Okay.
Okay, I'm okay.
Okay. So now we're going to simulate 60 hertz noise on ECG. When can we get ECG signals, first of all? Okay. Remember that we had a code that I gave you, which is the ECG demo. Remember that? This is the code that I gave you with the data. We have two data files, s118.mat and s119.mat. Okay. Basically, these files contain the data that look like, let's see here. ECG demo is not recognized. Not sure why. Change folder.
Run it, okay.
Okay. Maybe I'm in a different directory. Maybe in a different directory, different folder. It shouldn't be actually. Okay. Change. I'm not sure actually why, because actually this is just a demo program that we ran last time. Okay, let's load it again. Let's just close it from here and load it again from the. Remember last time I told you that basically this is the data file that you're going to see on Blackboard. Whenever you uncompress it, you're going to end up with a directory that is called ECG. Okay, and this will have. Basically, there are several files. Actually, it's only one file that comes out. Basically, I don't see it actually. Okay. Maybe this one. Oh, okay. It wasn't present. Actually, it changed the name. So the ECG demo. This is the file that you're going to see. This is the only example that you're going to see in the data that I gave you. You have two data files. It loads both data files and basically plots everything. See, not that. Okay. See here, for example.
5 figures or 6.
Yes. So basically, for example, this is the baseline wonder. Basically, this is the original ECG that you have, okay? So basically, what I'm going to do is I'm going to start with ECG demo and just take this signal here, okay, and add noise to it, okay? Add 60 hertz noise to it, okay? Let's do that together, okay? So I'm going to save that as ECG demo, leg 3, okay, so that you can recognize it, okay? Here I'm loading both data files. I need only one, so I'm just going to do that. And basically, I don't need these figures. I already have the data, so I'm just going to comment out these. This is, by the way, we're going to do that for all the experiments we're going to do. Okay, so it's just we don't need really the part where we plot the data, but actually we might plot them after we do whatever we want to do. But actually, we're just going to load the data, and then I'm going to start with signal equal to, I think it's 18 of 1 and range. This is the range actually that I selected so that I have a limited amount of data, so that because actually the record is very long. If you have the whole record, it's going to be very difficult to see. So this is the original signal. And then I would like to add 60 hertz noise. If you remember from what we did here, we simulated signal with frequency, whatever here, okay? So I'm just going to take the same thing here, that we did before, the simulated signal here, okay, and basically post it here. This is basically the original signal. And here I'm going to simulate the actual 60 hertz noise. Okay. Now the sampling frequency, the signal that we have, the sampling frequency for the ECG signals are 360. So I have to use this exact value here. And for N, I'm going to use exactly this number here. Okay, so that we have exactly the same number. Maybe we can put it here so that it's clear. So that we can change it also if you want to. And then say N here is equal to NP gas, same number, okay? And I need only one frequency. So basically, I'm just gonna put F1 is equal to 60. And basically, I'm just gonna call this sig N, which is noise signal. Okay, so the mixture, let's just call it sig X, will be equal to basically sig, the original signal, plus sig N.
Okay.
Okay, this is the mixture. This is the noisy signal. Noisy ECG signal. Okay. Just to make sure that I simulated everything correctly, actually there's one trick here, but let me just draw it like this first and then come back to this and show you why this is a problem. Okay. I'm just gonna take one of these figures and uncomment. The first one, I'm going to draw the sig signal. The second one, I'm going to draw the, actually not going to see much, sig N, okay. And here I'm going to just plot the summation, sig X, the summation, okay. This is sum.
What about the third one, the different doctor? There is original signal with the...
Actually, you don't need it. We already know what the difference is. The difference is sig N here. Okay, so basically this is the original, this is the noise, and this is the noisy signal, the summation of the two. Okay, because basically I added that to that. I added sig to sig N. Okay, so sig N is the noise here. So I already draw that here. Sig N. Okay. Actually, sometimes sig N, it's I'm not sure if it's a reserved word because it looks like sign. Sometimes this causes problems with Matlab, so I just call it sig N1. I should just avoid any conflict with a keyword that. Let's just draw that and see how it looks like. Let's close all, because actually there are so many figures. Okay. 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 Original signal. Okay. Okay. I remember. It looks like, of course, it looks kind of strange, but actually, sig is not just one on range. Actually, it should be. Let me check the S118. S118 is the 2 times this. Okay, so sig is 2 times 10,000, 2, which is kind of strange. It should be only 1 here. It's 1 in range. Unless I change that here somewhere. Oh, okay. So basically, I had that here that wasn't supposed to be there. Okay. This is the original, this is the noise, and this is the noisy signal. Do you see any difference between the noisy signal and the original?
Not
Actually,
really.
yes. Why? Because basically we added a noise with an amplitude of 1. See the range of amplitudes here? You're talking about hundreds.
Right.
So this one here will not basically be of any value. Basically, it's not going to affect the signal that much. So what I need to do is multiply the noise signal by a certain amplitude. Let's just say AN, for example, times this, and just set AN equal to
maybe 1,000.
1,000 will basically destroy the signal because it's going to be much larger. Let's just take it as 50 and try it. Noise, amplitude, and let's just say this is noise, signal, frequency. Okay, let's just try that. Okay. Actually, it's very clear now. See, whenever you have a thick line that looks like this, basically this means that you have very high frequency here. Let me magnify it for you to see it. See now? That thick line is basically the high frequency signal that we added to our ECG. Okay? So it's very clear here, right? It's very clear.
Right.
Very prominent. Okay, we would like to remove that noise. What should we do?
Filter.
It's a filter, definitely, yes. But should we use any type of filters? Which type of filter would be suitable for this? Basically, we can assume sometimes people think about the ECG range as basically have a bandwidth of 50, 100 hertz. But actually, you can have much lower bandwidth for the ECG and it would still be okay. So maybe you can get started with a filter, a low-pass filter. A low-pass filter that basically rejects anything beyond, for example, 55 hertz. Okay, and see what happens. Okay, you want to try that?
Okay, doctor.
Let's try that. Okay, we're gonna go to Filter Designer. Here we have 360. Here we have F-pass. Let's make it 50, and this is 55, so that we have basically beyond 55. Beyond 55, you're gonna get that much attenuation. And let's start with FIR first, and then we're going to try the IIR, okay? Are these okay? The 360 is the sampling frequency. You have to get that, by the way. You cannot estimate the sampling frequency. You cannot assume the sampling frequency, by the way. If you put another sampling frequency that is incorrect, you're going to get incorrect results, definitely, okay? Basically, the sampling frequency is a part of the data input that you will get, okay? So whenever you get data, you cannot say that I'm going to estimate the sampling frequency from the samples. You cannot do that. You have to get the samples, the sampling frequency in addition to the samples. So we're going to try that. This is just a regular low-pass filter. Now the order is about 102, okay? Which is almost very steep actually. But actually, let's just try it like this. I'm going to exactly do the same that we did before. So generate Matlab code. Let's call it lecture 3, 60 hertz, low pass filter 1. Okay. I'm going to also do the same thing. I'm just going to comment out the function here and basically go here, the part where I simulated my data, and just take that and go copy it here. So basically, it already computed the filter here in HD. I'm going to compute the simulated signal here, and then I'm going to apply the filtration here. Okay, I'm going to say sig f, the filter signal will be equal to filter of HD and sig x, the same thing that we did before. Here it doesn't make sense actually to plot the noise because actually it looks very noisy. It's basically, if you look at it, it's basically you don't see anything. If you want to magnify it, you can see inside the signal and all, but actually we know that it's a 60 hertz. Okay, so basically we don't really need to have the noise here. So basically I'm going to comment out that and replace it with the filtered signal. So I'm just going to comment out that and make the noisy signal as signal plot rakam number 2, and I'm going to add a signal here, signal F, as the filtered signal. Okay, so now I generated the filter here, I generated the signals here, simulated noisy ECG here, and applied the filter here. I'm just going to plot the output. Okay, subplots, see the number of subplots. Okay, okay, you don't have 4, you have
3, 1, 2.
yes.
Yeah.
1, 2, 3, it's supposed to be 1, 2, 3. How do you like that? Actually, it looks okay.
Okay.
Do you see the 60 hertz? Actually, you don't see it really. So,
Yeah.
but actually, the transient here, see the transient at the beginning? That's why you have a signal here, basically 0. So basically, that's why it looks that way. But actually, other than that, it looks clean. Okay, looks very clean actually. In order for us to see the effect of the filtering, maybe what we can do is either change the amplitude here to be larger and see whether there will be remaining parts of the noise at the output. Let's just put it as 200 even. So the signal will be extremely noisy. Let's see if the filter will be sufficient or not. Actually, it's still sufficient. See here, it's much larger, but still actually the output here is very much clean actually. Still okay. How about if we go here and make the attenuation of the stop band instead of 0.01, just make it 1. 0.01 was minus 40 decibels. Now I made it 20. Yes, 20. 1 over 10 is minus 20. Okay, let's try it. Actually, surprisingly, it's still okay. So it's still okay actually, because actually even it's 200 here, it became here about 20, so it's still okay. But if we change that amplitude to, instead of 200, maybe make it 500, 500 will basically overwhelm the signal, but still actually the output is still okay. It's very surprising actually. Let's try to magnify it a little bit and see if select. Okay, that's fine. You can just actually you can see that there are some residual noise here that is still present. Maybe you can magnify that a little bit even more, 1000. Just want to see the output becoming a little bit, see here, now it's more noisy. It's clearly more noisy in the output. Okay, so the stop band attenuation is very important. If you change the stop band attenuation and make it, instead of here, we made it 0.1, we're going to go back and have it as 0.01. Basically, you're going to see a clean output again. Okay, so actually 40 decibels or 1 over 100 is actually very good. Sometimes people think that you have to divide by 1,000 or 10,000 or 100,000. Many times, actually, it's not necessary to have that. Okay, so you have that for yourself. You have to try that for yourself and make sure that the attenuation that you have is sufficient. Okay, or whether you can actually reduce the attenuation, you will still get a good output. If you do that, you're going to end up with a filter that is more optimized. The filter will give you the function that you need without having to have a high order for you to do that. Okay, so now we can actually optimize. If you want to optimize this filter, what I would do is basically play with these fpass and fstop. So basically, the order here, I'm not sure actually, maybe you can just check it. The order is in N. N here is, actually it's not clear. Actually, it's overwritten here. So maybe I just put here N. No, it's not that. Actually, because actually we use N here and we use N here also. Okay, so the problem is that N is overwritten here. So if I wanted to know the N value, I have to print it here. So N is about 102 for this type of filter. Let's try the same thing with an IIR filter. This is 102, remember. Okay, I'll just select that as Butterworth. It's exactly the same specifications, and we're going to design a new IIR filter. The order now is less than half. We're going to take that, do exactly the same as we did with the FIR filter. Generate the design function. Let's use the same exact notation here, but I'll just add IIR so that you can discriminate between the two. This is the same filter design function. I'm going to do exactly the same as I did in the other one. So basically here I already did the work. So basically I'm just going to copy that last part here and plot the signal. So it's a different design function as you see here. It's very different here and there. But actually you can do exactly the same. The filter will come out in HD, and you do exactly the same thing that you did in the other filter. Let's see how it looks like. Here we have the amplitude. Let's just keep the amplitude as sane, 100 for example. How do you think that looks like? Would that be okay? You see that this is okay?
Yeah, maybe you can zoom in.
So there is noise in the beginning.
It's a little bit noisy, yes.
Yeah.
Okay.
Less than 1,000, there is more noise.
Yes, that's right. That's right. So basically you have more noise, a little bit more noise here, but actually what you can do is I can go back and change the order here. If I wanted to have the attenuation here as 60 decibels, okay? The order here will be a little bit more, but let's see how the output will look like. Actually, it looks cleaner. At the beginning, it was already noisy here, so basically it's okay. But in the other ones here, first of all, you see that there are some strange appearances here. See this part here, for example? Doesn't look right, right? You don't have something like that looks like this actually in your original ECG signal. So even though the general appearance of the signal looks okay, you have to be really careful when you're using IIR filter, because sometimes it doesn't look as good as you think. Okay, let's try it with 50 here. Let's try it with 50 here and the regular 40 decibels here. See here? Now it's not working. Now it's not doing the proper job actually. Okay. So basically for the IIR filters, you have to be really careful because sometimes you don't really get what you think you're getting. Okay. Don't really be happy with the order. Order here was, I think the order is incorrect. Maybe I'm printing in a wrong place. Actually, N should be from, oh, okay, there is no N here, sorry. So I'm not printing something that has any value actually. So basically, sometimes the filter does not work. Okay, maybe if you make it instead of 55, make it 59. Let's see if it works. Actually, it's still not working. You need to have more attenuation. Okay, sorry. I changed here instead of changing the amplitude, I changed the frequency. So basically, I fooled the filter. I actually designed the filter to filter beyond 50, but actually the noise is at 50. So let's try it again. I'm sorry. Okay, let's try it with the same parameters again. I was surprised actually to see that it's not working at all. It's usually not producing very good results, but actually they are okay, but they are not that poor. Now it looks okay. It looks very similar to that one. It's not very far, at least. If you change the stop band, if you change the transition band, and instead of having a transition band of 5 Hertz, make it 9 Hertz, actually usually helps. Actually, it helps here. It looks a little bit cleaner. And the order is likely to be smaller here. Okay? Do you get the idea? Do you get idea what we're doing? So basically what we have for the real signals that we're going to work with, what we're going to do is look at the signal, and instead of having the frequency of the artifact like what we had here, we actually here knew exactly the frequency that we basically wanted for our signal. Basically, for the noise, we knew that the noise is at 60 Hertz. Okay, for the actual artifact that we're going to work with, we really don't know that information. And basically, this will add a new part where we actually try to estimate that frequency and then experiment until we actually basically get it exactly the way it should be. Okay. I want to do one more experiment in this 60 Hertz noise. I'm going to try, if you remember, we have something called band stop filters or notch filters, if you remember. Do you remember band stop filters?
Yes, I remember.
Band stop filters. They look like, basically, if okay, so basically this is, for example, 0, this is 0. This is F1, this is F2, and this is infinity. This is the maximum frequency, okay? So basically, you're passing your signal here, multiplied by 1, and basically attenuating your signal here or multiplied by near 0. And basically, if you have your frequency, the desired frequency that you would like to remove here, it will be basically removed. So what we can do is to design a band stop filter, okay, with F1, for example, 55 Hertz, and F2, 65 Hertz. Okay, we can do that also with Filter Designer, and we can do it as FIR and IIR. Okay, so now I'm gonna change that to band stop. Whenever you have band stop, you have now you have to also put the sampling frequency, and you have F-pass1. And F-pass1 is the F1 that we were talking about. We'll just put it as 55. F-stop1, basically make it as 59. And basically F-pass2 is F2. Put it like 65. Here F-stop2 is like, put it like 61. And we put that here as 40, like what we had before. And we have the pass band attenuations, 1, 1 for both. So basically here you have a low pass filter, very, very much like what you had in the low pass filter. The cutoff frequency is 55 with a 3 dB point. Any point beyond 59 will be basically attenuated by 40 decibel at least. The other one is like a high pass filter. because basically the band stop is like a band pass, like a high pass and a low pass combined together, okay, multiplied together, basically added together, in other words. So basically here you have the cutoff frequency as 65. Below 61 hertz, everything will be attenuated by 40 decibels. Let's try to see how that filter looks like. See now how it looks like? Starts from 55 to 65, and at 60 you have really very strong attenuation here. Okay, because it's an IIR filter. This is an IIR. We designed an IIR by chance, okay, because you were standing here at IIR. The order here is 8, which is really good. Let's try to see what that looks like. Design it, basically generate the design function. Let's call it IIR band stop filter. ESF. Exactly the same as we did before. Okay, so you still have that here. Okay, still present in the memory. Okay, so let's try that. Here we have AN. Let's just take this as 100. 60 hertz here, correct? And this is 40. This is fine. Okay. How do you like the output? Looks very nice, actually, right?
Right. Very good.
And basically, if you compare it to the original signal, it looks very much like the original signal. And basically, you did that with an order of 8, which is really small. So that basically, you almost had no transient here. Transient is very small here, which is really good. Basically, this kind of experimentation is the thing that I would like you to try. I would like you to try something and basically try to investigate different types of filters. Try to investigate different parameters for each filter. And basically also, if you look at the filter design function here, you will find that each one of these filters will have actually different design criteria. Basically, you have different design functions here. Butterworth, Chebyshev, and so on. Okay, you can try these as well. Okay, each one of them might work in some situation and might not work in others. So you have to do that experimentally. You have to select the kind of filter that you're going to use, or the optimized filter that you're going to select based on experimentation, not on theory. Because in theory, you really don't know exactly how the filter artifact looks like. So what you're doing here is to try to fit the tools that you have to the problem that basically was given to you. Okay? Is that clear? So basically you can also do that as an FIR filter. Basically try to do that yourself from now to next time. Okay, so I'll leave the FIR filter. You just try the same thing, band stop filter with an FIR and basically try to do it yourself. Okay? Do you have any questions about that?
No, Doctor, it's okay.
Okay. So basically what we did now was we used something that has ECG in it. We wanted to have a signal that has ECG in it because basically we'd like to know the effect of the filter on our ECG signal. So for example, if I said that I'm going to use a low-pass filter with a cutoff frequency of 50, some people might think that the ECG might have more frequencies than 50. Okay, so when you see that the output becomes okay or comes out okay with an ECG signal, then this is a valid filter. Okay, if we have two sinusoidals like what we did last time, basically it's not really like the real signal. We're becoming close now to the real signal that we're going to work with. Okay, so right now what we're going to do for the rest of this lecture was just look at the actual signal. And basically, we're going to start with the first artifact, with the first type of artifacts, and try to estimate what kind of filter will be suitable for this artifact. Okay, so the way I'm going to do it is I'm going to start with the ECG demo, the original ECG demo. Okay, let's bring it here again. Okay, and basically look at the outputs for different. Let's see the one that has the. Okay, this one, or maybe this one is easier. This is 6, 4. Okay, okay, this one. So basically, this is the original ECG signal. Original means that this is the acceptable quality ECG signal that the doctor can use to make diagnosis. This is a very similar ECG signal. It's exactly the same one here, but with the baseline wonder artifact. This is the difference between the two. Okay, so now we would like to be presented with the second signal here, with the signal with the baseline wonder artifact, and would like to be able to come up with something that looks like this. We'd like to remove something that looks like this from the signal. So the first question that comes to mind, what kind of filter would enable us to remove something that looks like this? And why? We have to justify why we are selecting that particular type. Basically, this is just a question just to basically stimulate your thoughts, but it's actually, you have to actually think about it in a particular way that I'm going to tell you about right now. So first of all, if I compare this signal here to the original signal here, which one of these signals has more frequency? Which one has more low frequencies, and which one has more high frequencies?
The original has higher frequency.
Why would you say that? What's the reason why you chose that answer? How do you see frequency?
Yeah.
How do you see frequency?
The distance between peak and peak of each signal is closer than the noises.
Excellent answer. Actually, this is exactly the answer. Basically, if you think about this signal as a periodic signal, which is actually, this is very much true, it's close to being like that, then you see each one of these as a period of a periodic signal. When you see a signal that has a period that is very small like this, then it has high frequency. If you look at this, actually, what I would basically suggest that you do to understand the characteristics of this signal is basically assume that it's like a sinusoidal signal. Basically, it's not a sinusoidal signal, but actually, let's assume if it's a sinusoidal signal, okay? If it's a sinusoidal signal, in order for you to estimate its frequency, what you need to do is basically measure the distance between two peaks or two valleys, right? Right? This is the way we measure frequency in sinusoidal signals. So basically, if I wanted to estimate the frequency for a signal like this, basically, just look at this. Just the distance between this and this is almost like 300, right? Almost 300. 300 times 1 over 360, or let's just say it's 360. So basically, the period here, or the frequency here, the fundamental frequency of this signal is about 1 Hertz. How about this one here? The difference, if you say that we start from 5,000 and go all the way to 7,500. So it's 2,500 points. If you want to convert that to time, you multiply by S. TS is 1 over 360. Okay? So basically, this is going to be like what? Basically, you have 250. 2,500 from this one to this one over 360, which is going to be almost like 10, right? The period is going to be like 10, right? Almost. It's a little bit less than 10, but actually it's say it's almost 10 or 8, something like that. it's much larger than the one we've measured for ECG. The period is much larger, means that the frequency is much smaller. So the frequency here is almost 1/8 is going to be like 1.125. So basically, if I try to use a filter to filter a signal that is, say, 0.1 hertz from another that is 1 hertz, which type of filter should I use if I wanted to preserve the 1 hertz signal? You have, let me go to the
High pass.
Yes, it's exactly high pass. So basically, let me write it down here. You have original signal, 1 hertz, plus artifact, let's just call it baseline wonder signal. This is like 0.1 hertz. Okay, this is the mixture. Okay, if you want to preserve this one here and remove that one here, what you need to do is have a filter that looks like this. Basically, start from here. And this is basically the frequency axis. Okay, if you have something that looks like this, basically, and put this like 0.5 hertz, the 1 hertz will be here, the 0.1 hertz will be here. So basically, this will be gone, and this will be preserved. Is that clear?
Yes, sir.
Okay. This looks very crude, right? It's very crude, right? We basically just estimated something that is extremely crude. We actually didn't even get the exact numbers, okay? Let's try and take the signal. I'm just gonna do exactly what I did before. I'm just gonna basically design a high pass filter and just take it FYR. And I'm going to do that, 360. And the f-stop is, let's just make it like 0.2. And fs, let's just make it like 0.5, right? This is 0.5 and this is 0.2. And basically attenuation here, I'm gonna put like 40. I'm just gonna try to design a filter that looks exactly like this. Okay, let's see if it works or not. So let's design the filter first. Actually, because here it's very small because you have a large range here, but actually you can magnify it. Actually, you can't. I can't magnify it. But let's just try to get that filter and use it. The order, as you see here, is huge, right? How do you like that order? 1790, 1800 for a filter. It's extremely large, but let's just try it. Let's call it now leg 3, baseline wonder, HPF 1, okay? Okay, and I'm going to go to the ECG demo, and basically it's already there, I think, but it's I'm just gonna get that. Okay, maybe I can get it from the other one. It's easier actually, because I already did that here. I'm going to load that. The noise here is that. Okay. Okay. FS is already there. I think we should just get that. And basically, if you look at the ECG demo, the one with the baseline wonder, which is 3 here, it's called, it's baseline wonder 12, okay? It's 118, baseline wonder 12, okay? So I'm just gonna get that and create a signal, or basically make the signal equal to that. Let's just make sure. Signal 180, okay, that's fine. So the noisy signal, X, will be equal to this here, alt 1 and range, same thing. This is the noisy or baseline wonder artifact signal. And I'm going to do exactly the same as I did before, sig f equal to filter of sig x and or HD and sig x. Okay, and maybe I should just get the same figure that I had here. I had all the things that I wanted. I need that. So here is going to plot sig, which is the original signal, sig x, which is the noisy signal. Let's just put baseline wonder. Okay, and this is a filtered signal. Let's look at that. How do you like that? Actually, it looks great, to be honest. It's actually, look at this part here. Don't look at this part here. Transient.
Yeah.
And since we have an order of almost 1800, you have a transient all the way up to 900 at least. Okay, so basically, as you see here, this transient is extremely long because actually the order is extremely high. But the actual parts here, see, it looks actually better than the original, if you ask me. Actually, you remove the slight variations here that were actually, these are not real variations, by the way. They are acceptable, but they are still variations. So basically here you got something that looks extremely good from something that looks extremely crude, actually. And this is engineering, basically. As an engineer, you try to get very, very rough estimates to start with and see if it works or not, and try to optimize around them. I'm not going to stop there. I'm going to optimize around it. I'm going to try to change the cutoff frequencies until I get something that looks better, even better than this. I'm going to try to have to basically make the order a little bit smaller. These are optimizations, but actually I got some results. These are results very quickly using very simple methodology. And this is the kind of engineering that I would like you to basically start acquiring during this course. Okay, what we did again was that we looked at this, sorry, just bring it back here. We looked at the artifact that we needed to remove. We noticed that it has a low pass character relative to the original signal, meaning that if I wanted to separate that from the original signal, I had to have a high pass filter. I estimated roughly what the frequency of this artifact is like. I basically estimated the distance between this and that. But actually, you can try something different. You can actually estimate the difference between this and that, the location here minus the location here, okay? And see exactly what happens, okay? So basically, from this crude estimate, I started designing a filter and started experimenting with this filter. What I should do next is basically, with the same exact filter that I have here, I should just play with the parameters of the filter. I should play with the attenuation. I should play with the f-stop, with the f-pass, and things of that. So the thing that I have here in my filter, I can actually go back to the filter designer function, and instead of designing with equi-ripple method, these methods are used to estimate the parameters of the filter. There are so many different methods. It's beyond our course to start talking about these methods, but actually we just try them and basically use them as experimental validation, basically. We try different ones and basically validate the output from each one of them and see which one gives us a better result. Okay? So basically, what we did now, go ahead, please. Go ahead if you have a question. You have a question? Okay, So anyway, this is basically what I wanted to talk about in these lectures, these 2 lectures. I just wanted you to move from the point of just trying filters without really knowing what you're doing, without knowing what these filters actually do, to getting some theoretical background, to applying that to a known problem, to a problem where we know the artifacts and we can judge exactly what the signal output should look like and the artifact looks like. And basically now we started talking about the actual problems right away, basically. So basically now we started on our first part of the research problem. We now have filter for the baseline wonder artifact. What we need to do now is try to optimize the output for this filter. Okay, so first of all, this part here we need to get rid of somehow because actually it doesn't make sense. One very important aspect also is that you will find that the output here, if you, for example, look at this part here, this port is matched to this part here. These are actually corresponding to each other. If you look at this part here in the output, you'll find that it's delayed. And you'll find that it's delayed by basically half the length of the filter. Okay, meaning that it's 900 points delayed from the actual signal. So we'd like to take care of this delay actually. If we wanted to get the difference, to make sure that we remove the artifact correctly, we have to take care of this difference. We don't want to have a delay in this filter. So next time, inshallah, what we're going to do is to discuss something called the group delay. One of the characteristics of the filter is the group delay. Basically, you can find it here. Here we're plotting the magnitude response. You can actually plot the basically the phase response or the group delay. There's something called a group delay here. Group delay is basically something that looks like this. This is a group delay. There's a constant group delay. Okay, meaning that the output at a certain point will be 895 points behind the input signal. Basically, think about it this way. If you want to have enough length of your filter, of your signal, to compute the output from the filter, you have to have that many points. Okay, so basically, in order for the filter to compute the output, it needs that many samples to be able to do that. Okay, so basically, we're going to talk next time about this from the theoretical perspective and from the practical perspective, and try to find ways to get rid of this group delay. And we're going to do some more experiments with IIR filters for this artifact and compare the outputs between these 2 filters from the point of view of the response, of the actual quality of the output, and also from the point of view of the group delay, of basically the delay in the output of the signal. So do you have any questions for today's lecture?
Thank you.
Please, if you have any questions, yeah, go ahead.
For the actual problem of the ECG signal, actually we don't know the original signal, isn't it?
Actually, since you have in this problem, actually we know it because actually we are given that signal in the database. Because basically for us, this was given because researchers in engineering do not really know how an ECG, how a proper ECG looks like. So you may have seen an ECG that looks like this and you consider it still okay. Okay. So basically they gave us in the database for reference to all researchers working on this, we have the original ECG signal, and basically we can know from it actually how the artifact looks like. If you don't have it, if you have something that looks like this, but you know the ECG shouldn't have these variations, you can still do exactly the same as we did today. You can basically say that the ECG should be basically plotted on a flat line here, and we see variations here. So basically I see a peak here, I see a peak here, I see a valley here, I see a valley here. So I can estimate the baseline wonder frequency based on the variations of the actual signal. So I can still do that even if I have only the noisy signal. But actually, since the database already had the original signal, we basically looked at the artifact right away, directly right away. Any more questions?
Thank you, Doctor.
So basically, I'm going to post the code that all the codes that we did in this lecture, including the experiments that we did with different filters. And I'm going to also post the handwritten notes. If you have any question, if you try to run any of them and have problems, please don't wait until next time. Please send me an email and I will help you resolve the problem. Okay?
Okay.
And also, if you have any, basically, if you have a large part of the lecture that wasn't very clear, we can actually talk about next time. At the beginning of next time, please have your questions ready after you had some experimentation done like what we did in the lecture. The actual lecture will be also recorded, and it's going to be also on Blackboard so that you can look at it. I think Abdullah asked me about the where it is located. Actually, it's located in Blackboard. Actually, I cannot see it here, but actually there is a basically when you look at the maybe here, yes, when you look at that here, you have sessions and you have recordings. Okay, if you look at recordings, you will see the recording from last time here. Okay. But you're not going to see, basically the lecture from today is going to be posted in about maybe 6 hours. So maybe tomorrow morning it's going to be there, okay? But basically you'll have the lectures here that you can go through, and if you have any questions, please ask me, please send me an email and I will answer you, inshallah. Okay?
Okay, Doctor.
Okay, thank you very much, and inshallah I'll see you on Friday again. Again, if you want to change the schedule for any reason, if you don't feel comfortable with Friday, please agree on any time and I'll be fine with it, okay?
Okay, Doctor.
Okay, okay. Thank you, Doctor.
Shukran, thank you. See you inshallah. Assalamu alaikum.
See you. Alaikum salam.